What's up, guys? In this video, we're going to talk about all of the formulas and equations that you need to know as a respiratory therapy student. Are you ready? Let's go! I bet when you signed up for Respiratory Therapy School, you probably was not expecting to do much math, am I right? Because this is a healthcare program that teaches you how to care for patients with cardiopulmonary disorders. How much math could there possibly be? Well, if you're like me, you probably were pretty shocked to find out that there are in fact several formulas, calculations, and equations that you are required to know. If I'm being honest, I was not very pleased to find this out. But with that said, I do have some good news. Most of the calculations that you will have to know are in fact very simple. If, that is, here's the key, they're simple as long as you know the formula. If you know the formulas, the math is very simple because all you have to do is plug the numbers in and work it out. And in this video, we're simply going to cover all the formulas that you'll see in Respiratory Therapy School. Some are harder than others, but most are very simple. And I planned on doing a sample problem for each equation, but there are quite a few and that would be a very long video. So instead, I'm just going to cover them all individually in separate videos. But in this video, we're simply just going to walk you through the formulas. However, we do have a free ebook that you can get 100% for free on our website that does have an example of each and every formula, equation, and calculation. So in the book, we walk you through a practice problem for each and every one of these formulas. And like I said, it's 100% free, no strings attached. You can grab a copy from our website. I will drop a link down below in the description. But if you're ready, without further ado, let's go ahead and dive into the respiratory therapy formulas and equations. First, we have the minute ventilation, which is equal to respiratory rate times tidal volume. Then there's the alveolar minute ventilation, which is almost the same thing except you have to subtract the dead space. So it's respiratory rate times tidal volume minus the dead space. Then there's the airway resistance, or RAW. It is equal to the peak inspiratory pressure minus the plateau pressure divided by the flow. Mean airway pressure, or PAW. Mean airway pressure is equal to the inspiratory time times the frequency divided by 60. Then you multiply that by the peak inspiratory pressure minus the PEEP, and then you add back the PEEP. Work of breathing. Work of breathing is equal to a change in pressure multiplied by the change in volume. Alveolar arterial oxygen tension gradient, or P big A minus little a O2. This gradient is equal to the alveolar partial pressure of oxygen minus the arterial partial pressure of oxygen. So basically P big A O2 minus P little a O2. Alveolar oxygen tension, which is equal to the barometric pressure minus the water vapor pressure multiplied by the FiO2 minus the PaCO2 divided by 0.8. Arterial alveolar oxygen tension ratio, or A to A ratio. This is equal to the arterial partial pressure of oxygen divided by the alveolar partial pressure of oxygen. Arterial oxygen content, or CaO2. This is equal to hemoglobin times 1.34 times the oxygen saturation. Then you add that to the arterial partial pressure of oxygen multiplied by 0.003. And just so you know, in these content equations, the 1.34 and the 0.003 values are given in the formula. So these are values that you have to memorize. So moving right along, next we have the end capillary oxygen content, or CCO2. It is equal to the hemoglobin times 1.34 times the oxygen saturation. Then you add that to the alveolar partial pressure of oxygen times 0.003. Mixed venous oxygen content, or CVO2. This one is equal to the hemoglobin times 1.34 times the mixed venous oxygen saturation plus mixed venous oxygen tension times 0.003. Next we have the shunt equations. First we'll do the classic shunt equation, or QS to QT, and it is equal to the end capillary oxygen content minus the arterial oxygen content divided by the end capillary oxygen content minus the mixed venous oxygen content. And then you have the modified shunt equation. This one is equal to the alveolar partial pressure of oxygen minus the arterial partial pressure of oxygen multiplied by 0.003. Then you divide that by the arterial oxygen content minus the mixed venous oxygen content. Then you add that to the alveolar partial pressure of oxygen minus the arterial partial pressure of oxygen times 0.003. Whew! That one is a mouthful, and that's a big and ugly equation. But just a little hint, you probably won't see this one on the TMC exam, but you probably will be required to know it for some of your exams in school, so that is why we are including it here. But as I keep saying, the good news is it's very easy as long as you know the formula, because all you have to do is just plug the numbers in and you can easily work it all out. So let's keep going. The next equation is the arterial mixed venous oxygen content difference. This one is equal to the arterial oxygen content minus the mixed venous oxygen content. Oxygen to air entrainment ratio. This one is equal to 1 over 100 minus the FiO2 divided by the FiO2 minus 2, and that will give you the ratio. Arterial oxygen saturation estimation, or SaO2. This is equal to the partial pressure of oxygen plus 30. So you simply take the PaO2 and add 30 to it, and that will give you the estimated oxygen saturation. Next is the PF ratio, or PaO2 to FiO2 ratio. This one is equal to the partial pressure of arterial oxygen divided by the fraction of inspired oxygen, or FiO2. So it's just simply the PaO2 divided by the FiO2, and that will give you the PF ratio. Next is the oxygenation index. This one's equal to the mean airway pressure times the FiO2 divided by the PaO2, and you take that number and multiply it by 100. Oxygen consumption, or VO2. This one's equal to the cardiac output times the arterial mixed venous oxygen content difference. Oxygen extraction ratio. This one's equal to the arterial oxygen content minus the mixed venous oxygen content divided by the arterial oxygen content. FiO2 estimation for a nasal cannula. This is equal to 20 plus 4 times the liter flow. So if the patient's on 4 liters of oxygen, you would simply say 20 plus 16, and you could estimate that their FiO2 is 36% on 4 liters. Oxygen cylinder duration. This is equal to the gauge pressure times the tank factor divided by the liter flow. Liquid oxygen system duration. This is equal to 344 times the liquid weight divided by the flow. Cardiac index. This is equal to cardiac output divided by the body surface area. Cardiac output, or QT. That's right, I think you're a cutie. Anyway, the equation for cardiac output is simply the heart rate times the stroke volume. Then there's also the cardiac output with the fixed method, and this one's equal to oxygen consumption divided by arterial oxygen content minus mixed venous oxygen content. Cerebral perfusion pressure. This is equal to the mean arterial pressure minus the intracranial pressure. Mean arterial pressure, or MAP. This one's equal to the systolic blood pressure plus 2 times the diastolic blood pressure divided by 3. Next up is stroke volume. This one's equal to the cardiac output divided by the heart rate. Maximum heart rate, or heart rate max. This is simply equal to 220 minus the age of the patient. So if you have a 20-year-old patient, simply subtract 20 from 220, which would be 200. So their heart rate max would be 200 beats per minute. Heart rate on an EKG strip. So by looking at an EKG strip, you can calculate the heart rate simply by saying 300 divided by the number of large boxes between the R waves. Respiratory quotient, or RQ. This one's equal to the volume of exhaled carbon dioxide divided by the oxygen consumption. Next up is systemic vascular resistance, or SVR. SVR is equal to the mean arterial pressure minus the central venous pressure multiplied by 80 divided by the cardiac output. Then there's the pulmonary vascular resistance, or PVR. PVR is equal to the mean pulmonary artery pressure minus the pulmonary capillary wedge pressure multiplied by 80 divided by the cardiac output. Static compliance. Static compliance is equal to the tidal volume divided by the plateau pressure minus PEEP. Dynamic compliance. Dynamic compliance is equal to the tidal volume divided by peak pressure minus PEEP. Dead space to tidal volume ratio. A little shortcut to remember this one is PACO minus PICO over PACO, or more technically speaking, the partial pressure of carbon dioxide minus the end-tidal CO2 divided by the partial pressure of carbon dioxide. So just remember that one. PACO minus PICO over PACO. Children dosage estimation. So a child dose would be equal to the child's age divided by their age plus 12 multiplied by the adult dose. Infant dosage estimation. An infant dose would be equal to their body weight in pounds divided by 150 multiplied by the adult dose. Then there's the infant and children's dosage estimation using Freed's rule, which is the infant or child dose is equal to their age in months divided by 150 multiplied by the adult dose. Anion gap. This one's equal to sodium minus chloride plus bicarb. Body surface area. This is equal to 4 times the body weight plus 7 divided by the body weight plus 90. Next up is elastance. The calculation for elastance simply is the change in pressure divided by the change in volume. Smoking use calculation. To calculate the number of pack years, you simply say the pack smoked per day multiplied by the number of years smoked. So if a patient has smoked 2 packs per day for a 10-year period, their number of pack years would be 20. Suction catheter size estimation. The catheter size is equal to the internal diameter divided by 2, then you multiply that number by 3. Endotracheal tube size estimation in children. So the children tube size would be equal to their age plus 16 divided by 4. Next up is Boyle's law. Boyle's law states that pressure 1 times volume 1 is equal to pressure 2 times volume 2. Then there's Charles' law. Charles' law says that volume 1 divided by time 1 is equal to volume 2 divided by time 2. Then there's Gay-Lussac's law. This one states that pressure 1 divided by time 1 is equal to pressure 2 divided by time 2. Next up is Laplace's law. This one states that the pressure is equal to 2 times surface tension divided by the radius. Shifting gears just a bit, next up is Celsius to Fahrenheit temperature conversion. So in order to figure out the degrees Fahrenheit, you would say the degrees Celsius times 1.8 plus 32. And then switching that around, to do the Fahrenheit to Celsius temperature conversion. To get degrees Celsius, you would say degrees Fahrenheit minus 32 times 1.8. Then there's the Celsius to Kelvins temperature conversion. So to calculate for kelvins, you would say degrees Celsius plus 273. Helium to oxygen conversion, or also known as heliox. To calculate the actual flow that is being delivered, you would say the given flow rate times the factor. And just a reminder, if there's an 80 to 20 heliox mixture, the factor would be 1.8. If there's a 70 to 30 heliox mixture, the factor would be 1.6. But we'll cover all this stuff in another video. So moving right along, next we have the total lung capacity, or TLC. So there's 3 different ways to calculate the TLC. First one would be the inspiratory reserve volume plus the tidal volume plus the expiratory reserve volume plus the residual volume. So you just add all the volumes together, that will give you the TLC. The next one is, you would say the vital capacity plus the residual volume. And the third way is, you would say the inspiratory capacity plus the functional residual capacity. Then there is the vital capacity, which also has 3 ways to get this calculation. First is the inspiratory reserve volume plus the tidal volume plus the expiratory reserve volume. The next one for vital capacity would be the inspiratory capacity plus the expiratory reserve volume. And the last way to come up with the vital capacity is, you would say the total lung capacity minus the residual volume. Next up is inspiratory capacity, which also has 3 methods of calculation. First would be the inspiratory reserve volume plus the tidal volume. The next one would be total lung capacity minus functional residual capacity. And the third way to get inspiratory capacity would be the vital capacity minus the expiratory reserve volume. And the last formulas for PFTs is functional residual capacity, or FRC. To calculate the FRC, first you could say expiratory reserve volume plus the residual volume. Or another way to get FRC is the TLC minus the inspiratory capacity. Moving right along, we have the time constant. To get time constant, all you have to do is multiply the compliance by the resistance. Next up is the ideal body weight, or IBW. And in my opinion, this is the most important calculation for the TMC exam. And if you want to know why, I go into much more detail about this inside of our Hacking the TMC exam video course. So if you're interested in learning more about that, I will drop a link down below in the description. But for ideal body weight, all you have to do is say 50 kilograms plus 2 times the number of inches over 5 feet tall. So if you have a patient that's 5 feet 2 inches tall, you would say 2 times 2, which is the number of inches over 5 feet, which would give you 4, and then 4 plus 50 kilograms is 54. So for a 5 feet 2 inches tall patient, their ideal body weight would be 54 kilograms. Next up is the tidal volume. Simply to get the tidal volume, all you have to do is say the flow rate times the inspiratory time. Then there's the exhale tidal volume. The calculation for this one is the minute ventilation divided by the frequency. Then there's the corrected tidal volume. For this calculation, all you have to say is the expired tidal volume minus the tube volume. Pressure support ventilator settings. To calculate the pressure support setting, you would say the peak pressure minus the plateau pressure divided by the set flow. Then you multiply that number by the peak flow, and that will give you the pressure support setting. Next up is RSBI, or Rapid Shallow Breathing Index. To calculate the RSBI, you would say the rate divided by the tidal volume. And last but most certainly not least is the minimum flow rate calculation in mechanical ventilation. So to calculate the flow rate, you would say the minute ventilation times the sum of the parts of the IE ratio. So there you have it. Whew! That was a lot of formulas and calculations. And I know it seems like a lot, and it was kind of weird just going through these formulas but not actually providing an example. But as you can see, this video turned out to be very long just by reading through the formulas. So can you imagine how long it would have been if I would have actually did an example for each one of these like I planned to do? But like I said, I will break down each and every one of these in its own individual separate video at some time in the future, so be sure to subscribe so you don't miss out. And also, if you don't want to wait, you can grab the ebook from our website that has all these formulas and it has an example of each calculation. And the best part, it's 100% free. You don't have to pay anything, it's free, you can download it. Just go to our website, I'll drop a link down below in the description. Now you know all the formulas and equations that are required for you to know in respiratory therapy school. As I said before, the math is simple as long as you know the formula, because if you do, then all you have to do is just plug the numbers in. I will say this, there are a few calculations that you'll most likely see again when you take the TMC exam. Now we actually have a very unique strategy for this, for the calculations, but that's something we only share inside of our Hacking the TMC Exam video course. Our students are crushing it with their results after taking the course, so if that's something you're interested in, I'll drop a link down below in the description. And just a reminder, if you want to get the example problems for each and every one of these formulas and equations, be sure to grab the free ebook from our website. Thank you so much for watching all the way to the end. Hit that like button to support the channel, and be sure to subscribe for future videos. That's it for this one. Thanks again for watching, and I will see you in the next video. And as always, breathe easy, my friend.